Okay, gang, here's another example from section 2.6, number 25, and this says constructing an open box. Let's see, I have to lean over to see this. An open box with a square base is to be made from a square piece of cardboard, 24 inches on a side, by cutting out a square from each corner and turning up the sides. See the figure. And part A is going to ask us to express the volume of the box, this open box, as a function of the length of the side of the square cut from each corner. So are you seeing this? A square piece of cardboard, and we snip out a square corner from each of the corners and then turn up the sides to make an open box. Let's see that box, when we're done, looks sort of like this, right? It's a rectangular box, actually a square box, and we can see inside because the top is open. And then let's work on coming up with a function formula, the main part of the problem, part A, a function that gives the volume of this box as a function of the length of the side of the square that we cut out of the corners in order to make it. Okay, so if you can picture cutting out that corner and turning up the sides and think about what these dimensions look like, I guess the height of the box is going to be x, right? Can you read that? It's going to be awfully small on your screen. And the length of the base of the box, well, the original square was 24 inches long, and we cut a piece out of each corner that was a length x. So it's actually 24 minus 2 times x, and that would be this dimension too. I hope that's legible to you. So we get an open box that has a base that's square, and each of those lengths would be 24 minus 2 times the length of the square we cut out of the side, and then it would have a height that would be whatever the length of the corner of the square corner that we cut out of the side. And the question in part A is, can you come up with a volume function in terms of that length x? I'll try to write large, okay? So in part A, I'm thinking the volume of a rectangular solid, the volume of a box, is length times width times height, right? It's multiplying the 3 dimensions together in order to get cubic units. This doesn't get me very far, though, in the direction of a function that I'm asked for, because I need to have volume as a function of x. X has to be the only variable that's in my function. And recall again that it might be helpful, besides using capital V to stand for volume there, to make sure you're understanding that the input variable should be this dimension, this height x. Okay, so V of x. I need to enter the length and the width and the height all in terms of x. And luckily I've got that worked out right here. So basically 24 minus 2x times 24 minus 2x, and multiply this all by x. Okay, so here's volume expressed in terms of just x, right? Length times width times height. That would actually answer part A. I'd like to clean this up a little bit. If I want to write this in another form, I'd multiply these two binomials out. I've got to use FOIL. 24 times 24, and then I do the outside product, negative 2x times 24, negative 2x times 24, and then negative 2x times negative 2x. I'm going to spare you writing all of that out. I did that a minute ago, and I came up with 4x cubed minus 96x squared plus 576x. I had to multiply out the two binomials and then multiply through by x. And I rearranged the terms as well to write them in descending powers of the variable. So I get this, polynomial. And that would be a good answer to part A there. Let's see what else we're supposed to do. Part B, what's the volume if a 3-inch square is cut out, and what is the volume of the box if a 10-inch square is cut out? So in part B and part C, essentially, I'm supposed to figure out what volume is when x is equal to 3 or 10. In other words, what's v of 3? What's v of 10? And I could take 3 and 10 and put them back into this formula. I could even go back to the original here and put in x, put in 3 for x every place I see it, or 10 for x, and simplify. But let me go on to part D. It says graph the volume function, and for what value of x is v largest. Okay, so I put this in my calculator, and I generated a graph. Let's see if I have that in here. That looks like this. Oops. Okay, now there's a little bit of work in this that I noticed as a challenge to some of you based on the test. You get the function formula in there, but then you have to experiment in order to find a window where you can see all the features of the graph. So this has a maximum x value of 15, I believe, and it has a maximum y value of 1,200. So without a little bit of zooming out and experimenting, you're not going to see the features of this graph. If I think about what the natural domain in the problem situation for x is, I can't really cut out a square that's smaller than 0 inches on a side, so I think x has to be non-negative. And there'd be a maximum value as well, because I've got a square that's 24 inches square, and I can't cut out corners that are any bigger than 12 inches, if you see what I mean, and still have any material left. So actually, my domain here really in the problem situation is going to require that x stays somewhere between 0 and 12. It's going to be someplace in that loop that's above the x-axis. All right. To answer parts B and C a shortcut way, let me just press trace. I know a number of you would use the second calc value for this. If I'm in trace mode and I just hit 3 enter, it's going to take me right there on the calculator screen. It's going to move the cursor to where x is equal to 3, and it says y is equal to 972. So however I did this, oops, lost my pen, I would get 972 cubic inches, right? If those dimensions aren't inches, the volume would come out in cubic inches. If I tell the calculator 10 enter, it's going to move the cursor over here. Did I lose it? Oops, I put in something else. 10 enter. It's going to move the cursor over here to the point 10, 160. Cubic inches. I guess it's pretty clear to see from the graph that there's a spot where I can get a higher volume, right? Where is that local maximum? And that's what they're asking for in part D, for what value of x is v largest. So I'm going to use second calc max. Left bound, right bound, guess. And it's going to tell me that my maximum occurs when x is 3.99999, and at that point y will be equal to 1024. Maximum volume 1024 cubic inches when x equals 3.99999, 4.0 inches. Bye-bye.